Welcome back to mass transfer operations 2. We were discussing on membrane separation processes. Now, we will be discussing the last topic of this mass transfer of membrane separation processes, that is Micellar-enhanced ultrafiltration. The name itself suggests that the ultrafiltration process will be enhanced by micelles. So, micelles are actually formed using surfactants. So, now we will be discussing about how surfactants will be enhancing the separation process for ultrafiltration operation. So, before that we need to learn something about the application of surfactants in separation processes, like say if we talk about the processes with full scale commercial utilization. So, that is we can say flotation is there. Okay. When we will be talking about the processes with some commercial application, so there are like adsorptive bubble separation or liquid membranes are there. And whenever we will be talking about these laboratory processes with a high potential, the first one is this micellar-enhanced ultrafiltration. That is in brief it is a MEUF. Then we have this cloud point extraction CPE. Then we have surfactant enhanced carbon regeneration CECR. Okay. So, now we will be discussing about the surfactant based separation processes in detail. So, before that we need to understand the meaning of this surfactant, or we can say this surfactants are surface active agents. Okay. There are generally 3 different types of surfactants, like ionic surfactants are there. Maybe say we can say this ionic head and non-ionic tail will be there. Example is suppose this SDS, sodium dodecyl sulphate, or cetyl pyridinium chloride, or so many. And then we have this non-ionic surfactants. These are non-ionic in nature, like say polyethoxylates. Then third type is say zwitter ionic surfactants. We can say these are having both ionic and non-ionic characteristics, like we can say sodium lauroamphoacetate like this. So, and there are so many we can say ionic surfactants, non-ionic surfactants, and zwitter ionic surfactants. Many surfactants are also edible in nature. In so many food grade products also some ionic surfactants also are used to stabilize the say food grade products or to preserve for a long period of time. But here we will be discussing about the any separation process which is related to surfactants. Okay. And especially in ultrafiltration process we will be discussing the role of this different surfactants, both ionic means cationic or anionic surfactants, or we can say both cationic and anionic in a whole, say how these are contributing towards the separation in the ultrafiltration process. Okay. So, the ionic surfactants are of 2 types. We told this previously, that suppose cationic surfactant like cetyl pyridinium chloride, where we can say this one chloride is minus and then cetyl pyridinium is the cationic part. So, these surfactants have positive charged heads when put in the aqueous solution. So, negatively charged particles will be attracted by these positively charged heads. For anionic surfactants like say sodium dodecyl sulphate, these surfactants have negatively charged heads. So, when it is put in the aqueous solution. So, if we want to separate this we can say positively charged particles, then we shall go for this anionic surfactant mediated ultrafiltration process. Okay. In aqueous solution, so we can say the CPC, that is we can say cationic surfactant will be separated into Cp plus, cetyl pyridinium plus and chloride minus. This Cp plus actually cetyl pyridinium plus will attract these negatively charged solutes. Okay. For SDS, say it will be dodecyl sulphate part will be minus and Na plus will be there. So, this dodecyl sulphate part will attract the positively charged particles from the aqueous solution. Okay. Now, we need to understand the factors that influence the solubilization of the charged particle or the particles which will be separated using the surfactant mediated separation processes. The first factor is this structure of the surfactant. So, we till now we have learned that the types of surfactants are of like ionic surfactants, then non-ionic surfactants and deuterionic. So, in ionic we have cationic and anionic. So, what type of structure of the surfactant is there, or we can say this one, if it is a cationic surfactant, what is the bulkiness of the cationic part, or what is the bulkiness of the anionic part of the anionic surfactant, or whenever the surfactant will make the micelle, or we can say this one will make the globule. So, above the critical micellar concentration, we will be discussing in detail about that. So, what type of shape actually it will create. So, that controls the solubilization of the solute particle, or we can say this one separation of a particular target component using the surfactant. Then structure of the solubilized, or we can say this one target component. What is the structure of the target component? If we talk about this cationic surfactant or anionic surfactant, then the structure of the target component or solubilized should be opposite in nature, or we can say this top surface should be oppositely charged. So, that this will be coming in closer or in contact due to the electrostatic force of attraction. Okay. Then third factor is this effect of electrolyte. So, in each electrolytic solution, the target component or solubilized is there, and also the what surfactant actually is added inside this electrolyte. Okay. So, depending on the polarity of the electrolyte, say we can say the separation, or we can say the stabilization of the target component as well as this surfactant will take place, and accordingly the separation will take place. Then effect of monomeric organic additive. So, that is also required in some surfactant mediated separation processes. Some monomeric organic additives also are added. These will say trap this target component, it will try to help to be trapped by the surfactant, this one with the help of that additive like this. Then effect of these polymeric organic additives also. Okay. And then effect of temperature. So, if the process is endothermic in nature, say, then we can say this one with the addition of temperature the process will be very forward. If the process is very exothermic, then we can say at the lowering the temperature the process will be favorable. Okay. Now, we need to understand the meaning of this critical micellar concentration, because you see for micellar-enhanced ultrafiltration or surfactant mediated separation processes, we need to understand the concentration of the surfactant above or below the CMC or critical micellar concentration. So, when surfactant monomers are dissolved in aqueous solution, the hydrophilic heads actually point towards the friendly aqueous solution. Suppose say this is the aqueous solution like this. So, we can say this hydrophilic heads are all heading, or we can say this one pointing towards the friendly aqueous environment, and hydrophobic tails actually will be towards the air. So, we can say this one hydrophobic tails will be we can say spread towards the air like this. Okay. So, only for the stabilization of the micelles like this. So, when beyond a particular concentration of the monomer, these form the globules and enter into the bulk of the solution. So, we can say this one globule will be formed, where we can say this way, say hydrophobic tails actually will be concentrating inside this we can say the aqueous solution only to be stabilized. So, it will make a sphere. Okay. So, these globules or agglomerates of the monomers are of spherical in shape to have the minimum surface energy, because in that case only we can say this one as the surfactant is dissolved in aqueous solution. So, we can say this one have minimum surface energy. So, it will try to be this one stay in the we can say globular form, or we can in the spherical form. So, this sphere actually is called micelle. Okay. So, so many micelles actually will be formed when the surfactants will be dissolved above the with their critical micellar concentration. So, this concentration of the surfactant is known as critical micellar concentration, then or in brief it is called CMC. Okay. The typical micellar diameter varies from 2 to 10 nanometer depending on the bulkiness of the surfactant we can say bodies. Okay. There exists a size distribution of the micelle. So, we can say this, it is not that always the size of the sphere will be uniform. So, these may be varying in a wide range. Okay. So, the CMC of the sodium dodecyl sulphate is 8.1 millimolar and molecular weight of the SDS is 288. Okay. Whereas, the CMC of the cetyl pyridinium chloride is 0.88 millimolar. Okay, this very almost 10 times lower than SDS, and molecular weight of CPC monomer is 340. For non-ionic surfactant, the CMC is very small. Okay. Now, we need to learn the how to determine the critical micellar concentration. So, you see, whenever we have the monomers in the dissolved form in the aqueous solution, then these will try to be accommodated in a spherical shape, and then the minimum we can say surface energy will be obtained, and that is why say the physical properties of the micelle will be changing drastically when it is in monomer and when it will be converting into the we can say micelle. So, it may be noted that various properties means the physical properties of the solution changes we can say this one around the CMC concentration, and surface tension drastically decreases actually beyond the CMC level. Osmotic pressure and conductivity of the solution increases slowly beyond the CMC. So, some of these typical variation of the surfactant concentrations are we can say this one are shown in this figure, like we can see the surface tension values will be remain almost invariant, and when it will be forming the micelle, then drastically the surface tension value will go on decreasing. So, because that time the so many surfactants actually monomers will be agglomerated, like this osmotic pressure also it will be increasing slowly, and once it exceeds its CMC value, then the osmotic pressure value will not increase drastically, and there are so many parameters. So, we can say this one there is one concentration beyond this. So, we can see all the properties will behave differently from the properties below this concentration. So, that particular concentration actually we can say this one is CMC, critical micellar concentration, or we can say this one when the micelle will be formed inside this aqueous solution, their physical properties will change drastically. Okay. So, therefore, measurement of such properties can lead to the determination of CMC by observing the surfactant concentration where the slope of the curve changes. So, we can say this one the particular concentration of the surfactant is termed as the critical micellar concentration. And if we want to use this concept to separate the solute particles from the bulk with the help of this membrane, then our surfactant concentration should be well above the CMC, so that the monomers will be forming globules, and then the globules will be attracting the solutes, and then with the help of this bigger pore diameter containing membranes, we will be able to trap the small diameter solutes, and that is the beauty of the micellar-enhanced ultrafiltration process. Means the molecules with the nanometer range will be separated by ultrafiltration membranes, that is why the throughput will be very high. Now, whenever we will be discussing about the micellar-enhanced ultrafiltration, so in this case of we can say anionic micelles like sodium dodecyl sulphate, the outer surface of the micelle are negatively charged. So, because that is why it is an anionic surfactant, and for cationic micelles we can say the outer surface of the micelles are the positively charged. Now, in case of the oppositely charged pollutants present in the system, for example, we can say the cations like zinc plus 2 plus, then cadmium 2 plus or arsenic 3 plus, etc., they will be attached on the outer surface of the anionic micelles of the SDS. So, we will be preferring this SDS to separate the metal ions, okay, because these are anionic surfactants. The top surface of the micelle will be of the negatively charged, where the metal ions will be of the positively charged. Then due to this electrostatic force of attraction, the metal ions will be attached on the top surface of the micelles, and these will not pass through the highly porous ultrafiltration membrane. If we do not use these surfactants, or we can say this one, if we do not use the micelles, then all the metals actually will be passing through the ultrafiltration membrane. And for anionic pollutants like we can say cyanide or manganate, or we can say the dichromate or any other these anionic we can say pollutants, these will be attached to the cationic micelles of cetyl pyridinium chloride or cetyl this one tri isobenzyl bromide or so many other anionic surfactants. by only electrostatic force of attraction. Okay. So, therefore, for removal of cationic pollutants the anionic surfactants are required, for anionic pollutants cationic surfactants are used. Okay. If there are some non-ionic or organic pollutants present in the solution, they can be dissolved within the hydrophobic core of the micelle. So, that we will be discussing also later on. So, if we have some non-ionic or organic pollutants, or we can say this one some pollutants with the slightly delta positive or delta negative charged on the top surface, these will be we can say dissolved inside the core of the micelles only due to the presence of the we can say this intermolecular space inside the we say globules. So, now the transfer of the pollutants from the solution phase to the micelle is we can say is almost instantaneous, because the concentration of the solute inside the micelle is 0, whereas the concentration of the solute in the bulk is in concentration at the concentration of the solute concentration at the bulk. So, due to this Cb minus say C micelle, that is actually we can say the driving force is entirely the concentration gradient or whatever the solute concentration is present in the bulk. So, due to that we can say this one the pollutants will be transferring instantaneously when the solution surfactant solution above CMC will be dissolved. But one point actually we need to mention here, that if the surfactant also is above the CMC values, some monomers also will be present on the we can say surfactant solutions. So, micelles being larger in size like these nanocolloids, their sizes also increase with the solubilization of the pollutants, or we can say this one whenever the pollutants will be attached at the top surface due to this electrostatic force of attraction, the size of the micelle will go on increasing. At the same time, if the solutes are dissolved or we can solubilized inside the core of the we can say micelles also, then all the size also of the micelle also will go on increasing, and the one time will reach when the we can say the it will exceed it we can capacity limit, then the micelles will not be able to separate the particular we can say this ionic or non-ionic or organic pollutants for using this surfactant mediated separation processes or micellar-enhanced ultrafiltration process. So, these large agglomerates can now be separated by more open pore sized membranes like this ultrafiltration at the expense of low pumping cost. So, the metal ions which were able to separate by either this reverse osmosis membrane or nanofiltration membrane, now will be this one will be able to separate using this highly porous ultrafiltration membranes, because the micelle will attract the metal ions and then the micelles will not be allowed to pass through the we can say this one pore of the ultrafiltration membrane. The micelles will solubilize will be with the solubilized pollutants are retained by the membrane, and the filtrate will be devoid of the pollutants and has the surfactant concentration to the level of CMC, which is generally extremely low. So, we can say this one as the CMC or critical micellar concentration of the surfactants are always very low. So, at the lower concentration the surfactant will be able to separate the ionic particles, especially suppose metal ions or any anionic part like permanganate or dichromate, cyanate etc. With the expense of a small amount of surfactant. So, in fact, there are methods exist to remove the leftover surfactant in the filtrate stream by suitable chemical treatment. We will be discussing also the beauty of the surfactant mediated separation process is that once the process is over, whatever the surfactant actually will be coming out through this retentate or permeate will be recovered, and that can be used again for the same process. Like this is the mechanism of MEUF, like this below CMC value, suppose surfactants are all these are in the monomeric form. So, it is not able to attract so many we can say solutes very easily, but whenever it is above CMC, then you see the solutes are trapped inside this one, and if we say if it is like positively charged, the globules are in the positively charged, then say negatively charged will be say we can say this attached on the top of this one, or the reverse one will be if the surfactant is negatively charged, we can say anionic surfactant, then cations will be attracted and it will form a layer this above the anionic surfactant. Okay. And now you see this one, suppose the solutes are now trapped inside this we can say CMC, we can say this micelles. Suppose the solutes are trapped, now this is the membrane, the big pores, but you see remember this one, the pores of the suppose ultrafiltration membrane much more higher than the size of the solute, but due to this electrostatic force of attraction of this micelles, the solute actually will not pass through this one. That is why the solute passage is not present here, but you see this I mentioned earlier also that some monomers actually of the surfactant will be passing through this membrane, but that is very negligible, and we will be discussing that these will be separated very easily. And this is the we can say this one image of the micellar-enhanced ultrafiltration. These are we can say this one micelles of the surfactants, and these are able to trap the we can say either cationic or anionic or non-ionic or organic pollutants this one efficiently. Now, this is like say we can say this one cetyl pyridinium chloride, that is the positively cationic surfactant, and this is sodium dodecyl sulphate, that is we can say anionic surfactant. So, you see this we can say these hydrophilic heads are now their tails are there concentrating inside this we can say globule, and then we can see this one hydrophilic heads are heading towards the outer surface of the micelle. So, it can attract we can say this one so many anionic pollutants like this chromate or manganate or cyanide etc., and at the top surface like this, and which are we can say non-ionic in nature, these will be trapped inside this one. For sodium dodecyl sulphate, say we can say this one metal ions will be attracted on the top surface of the SDS globule. Okay. So, whenever we will be talking about this membrane, the pores are very big, but you see due to this attraction of the these one charged particles with the surfactant micelles, these will not be passing through this one. Okay. So, we can say this one only some monomers will be passing, and that is why the efficiency of the micellar-enhanced ultrafiltration is much more higher than any say ultrafiltration process, even the nanofiltration process also of the same solute. Now, we will be discussing three different cases. So, one will be like MEUF using cationic surfactant, then we will be discussing about the MEUF using anionic surfactant, and third one we will be discussing MEUF using this both cationic and anionic surfactants. So, mixed surfactant also will be using to separate the different cationic and anionic parts. Okay. Firstly, we will be discussing about the MEUF using these cationic surfactants. So, this is the schematic of the MEUF process using this cationic surfactant. Suppose feed solute is there inside this aqueous solution, and we have added the surfactant above CMC value. Then as we discussed earlier that the feed solutes will be attracted by these cationic surfactants. Then we will be using this MEUF process. Then we have two different parts, one is the retentate, another is this permeate. Okay. This retentate will be with more the surfactants, because you see as we have added surfactant above CMC. So, it is presumed that the most of the monomers are now converted into the bulk, this one above this micelles concentration, though they have formed the micelles. So, the micelles will be there with the retentate, and then we need to use this one again with some treatment or without treatment also. But whatever the permeate actually we are getting, maybe it may contain some amount of the surfactant along with the minimum amount of the target component or solute. So, we will be going for this first chemical treatment 1 with the help of potassium iodide, and then we will be first we will be trapping these monomers, or if there some these micelles are there, these will be trapped by potassium iodide, and then we will be regenerating in the chemical reaction 2 scheme using copper chloride to give this again cetylpyridinium chloride, we will be discussing this one, and during this chemical treatment process 1 using this potassium iodide, whatever the filtrate actually disposable filtrate will be there, we need to discard this one, we will be discussing this later on. Say like this is the membrane cell and we have this feed tank, inside this feed tank suppose we have this solute and we have this surfactant, say cationic surfactant we have. Okay. Suppose say CPC is there or surfactant is there, then this through this pump it will enter into the membrane cell, then from the retentate line we can say this one solute, we can say the globules of the surfactant will again come back to the this one we can feed tank. But whatever the permeate actually will be this one coming out, some portion will be going for sampling and some portion will be recycled actually after this treatment. Okay. But the bypass line is there to control the flow rate through this membrane cell. Okay. Now, this is the typical example of the Micellar-enhanced ultrafiltration process using this cationic surfactant. The example this figure actually is given here only to make us understand that say whenever we have this for any batch process, suppose the surfactant concentration of cetylpyridinium chloride is 10 kg per meter cube. So, that is above the CMC value. So, then you see the for the some pollutants like paranitrophenol, metanitrophenol, then phenol, catechol, beta-naphthol, orthochlorophenol. So, all these case whenever we have this without the any surfactant, there you see observed retention values are always less than 30%. It indicates that size of all the organic compounds are so small that through this 1000 Dalton membrane, that is the ultrafiltration membrane, all the solutes are passing, almost all the solutes are passing, means only rejection rate is maximum 30%, but after say we can say this one 1750 second, the most of the cases you see the observed retention values goes beyond 7 or 8%. So, all these are permeating through the membrane, because it is obvious thing that the size of all the organic compounds are below we can say this on 350 or like this. So, that is why these are not retained on the membrane surface. But once 10 kg per meter cube CPC cetylpyridinium chloride is added to all of these suppose these all the organic pollutants, then you see the retention values are now shooting up to say from 7% to we can say this one around say in some cases it is almost 98-99%, whereas for few cases only it is almost up to 70%. So, from 7% to 95 or 96% retention value increase is only due to the formation of the micelle of the cetylpyridinium chloride, and as it is a cationic surfactant, and that is why all these organic compounds are now trapped on the surfactant micelle. But one point is that say whenever we will be talking about the permeate flux values or throughput of the process, then the trend is reverse. Whenever we have this only pure we can say this one organic compounds, their permeate flux values are very high, because there is no globule or there is no resistance, but whenever the surfactant is added, then the flux values are decreased. But here if we compare this we can say rejection with these flux values, then rejection values were more than 10 or 15 times, whereas the flux values are decreasing by only we can say this one 2 times. Means say this whenever we will be adding surfactant, then flux values will be decreasing suppose from 9 meter cube per meter square second into 10 to the minus 6 to it is coming out at around say 4 or like this. Okay. So, now the one important point or we can see the beauty of this micellar-enhanced process that we can recover the surfactant from both the permeate and retentate, and these will be reused for the system. So, the first treatment process we whatever we mentioned from the permeate like this, we need to add the potassium iodide, because suppose cetyl pyridinium chloride was there in the permeate either in the monomeric form or in the globule form. When it will be reacting with potassium iodide, then it will be forming this cetyl pyridinium iodide, that will be precipitated out, and then potassium chloride will be there in the aqueous solution. Now, whatever the precipitate actually we have cetyl pyridinium iodide, we need to add copper chloride to get back this CPC. So, that CPC is nothing but the CPC what we used for the previous this one separation process, and copper chloride will be precipitated out and iodine will be liberated. So, this whatever the CPC will be generating from the second chemical treatment process, that will be again used for the next micellar-enhanced ultrafiltration process. And we have observed that above 90% surfactants were recovered using this reaction, two reactions in chemical treatment process 1 and followed by chemical treatment process 2. Okay, so, this is we can say this one whatever we discussed like this for chemical treatment process 1, you see the CPC recovery was more than we can say 99% in all the cases whenever we have we can say eosine, para-nitrophenol, beta-naphthol, potassium dichromate, potassium permanganate like this. For all the cases you see percentage removal by combination of MEUF and precipitation like this with respect to MEUF feed. So, the CPC recovery was like this above 99%. So, in this case whenever CPC is used for the separation of organic pollutants, then the recovery of the CPC from the permeate is above 99.9%. So, we can say this almost 100% CPC is recovered, and it is observed that the usage of this recovered surfactant is feasible, and the properties of the surfactants are similar to that of the pure surfactant as well as the recovered surfactant. Whenever we will be doing this one in the treatment process 2 like this regeneration also, for these cases for eosine dye or para-nitrophenol, beta-naphthol and potassium dichromate, potassium permanganate, the CPC recovery is to some extent lower like this, it ranges from we can say this on 77% to we can say this one around 84%. So, here actually you see recovery of the we can say this one by chemical treatment 1 and 2 with respect to we can say permeate MEUF permeate, it is to some extent lower, but overall we can say this one we are able to recover the surfactant which is coming out through this permeate, and that can be reused. Now, we will be discussing about the MEUF process using this anionic surfactant. They are almost similar, only the difference is that in place of the cationic surfactants or organic solutes, now we will be able to separate these metal ions like this. So, it is we can say this one the same thing, feed contains surfactant as well as the solutes, then we will be doing this MEUF process. Then whatever the permeate will be there, unsolubilized solute and surfactant will be there, we will be doing the chemical treatment process using this calcium chloride to separate the sodium dodecyl sulphate in terms of calcium dodecyl sulphate, and it will be precipitated with then this calcium dodecyl sulphate will be regenerated using sodium carbonate to get the surfactant rich filtrate, that will be reused for the next MEUF process. Okay. And there will be disposable precipitate, these will be discarded. Now, this is the pictorial representation of the separation of the we can say this metal ions, or we can say this one organic pollutants like this using this anionic surfactants. Like this the top surface of the anionic say micelle is like this negatively charged. Then we have this suppose either copper or calcium plus, these will be sticked on the top surface. This is the membrane surface, the one gel layer will be formed, and then through this membrane only water should pass, but we told this one that it is not that above CMC some monomers will be there in the surfactant solution. So, this will be passing through this membrane. and along with the small amount of feed these solutes. Okay. So, so whenever we will be say we can say we have these different say organic compounds like this beta naphthol etc. So, these will be trapped inside these globules, and then say after this membrane separation process some monomers will be coming out, and which are not trapped by these globules, or we can say this one which will not be trapped by the micelles will be coming out as the we can say this one CP. Okay. So, here also the schematic representation of the we can say this one permeate flux value and the retention using the sodium dodecyl sulphate as the 25 kg per meter cube. This is above the CMC, and we are assuming that most of the monomers are now forming globules, and it is able to trap all these copper, calcium and beta naphthol. That is why you see retention values of all these are always around say more than say 90% for all these cases. Okay. But the flux values are you can say this one I told earlier also that whenever we have these surfactant solutions, then the flux values will be to some extent lower than the actual flux values. Okay. So, due to the we can say this one generation of the small gel layer over the membrane surface. Now, the regeneration of the SDS this one we can say the from permeate and retented like this. So, this is the SDS and this is calcium chloride in the aqueous solution, then it will be forming calcium dodecyl sulphate, that is we can say precipitate, and sodium chloride will be there in the solution. In the second reaction we can see the second chamber will be converting this calcium dodecyl sulphate into sodium dodecyl sulphate, which is nothing but the surfactant that will be used for the next process. Okay. So, we will be able to separate that this sodium dodecyl sulphate from as in the form of calcium dodecyl sulphate to again sodium dodecyl sulphate. Now, this like this is the schematic presentation of the chemical treatment 1 like this surfactant precipitates like this. So, the equation also indicates that the first equation like this 2 moles of surfactant actually reacts with 1 mole of calcium chloride. So, here also you see whenever we have this almost 0.5 the ratio between this calcium chloride to SDS, it is giving this almost more than 90% SDS precipitation. This is as per the equation, or we can say this one their stoichiometric ratio. So, it is also observed here in presence of the different metal ions, or we can say this also beta naphthol also these organic pollutants, because when the organic pollutants will be there, so these will say we can say utilize some of these surfactants in the form of these we can say globules, there it will be strict. So, for that case we can say the effectiveness or we can say regeneration of the sodium dodecyl sulphate is not 100%, because some portions remain also in the we can say this one utilized form with the metal ion which is coming out from the through this permeate, and that is why we can say this one here also we have got for we can say this one almost 1, because this equation also is 1:1 for this one calcium dodecyl sulphate and sodium carbonate, this is 1:1. So, it is we can say this whenever ratio will be 1:1. So, in that case we will be able to get almost 95% sodium dodecyl sulphate back. Okay. So, these are the we can say this one in the tabular form this how much we can say this one SDS will be recovered for this say suppose copper, calcium or copper beta naphthol, or we can see this copper beta naphthol and paranitrophenol mixtures, or we can see this copper beta naphthol, paranitrophenol and aniline. So, in all the cases we have seen that the SDS recovery overall SDS recovery is around say ranging from 87 to 95%. So, that is we can say this one huge, and as we know the cost of this SDS is very high. So, how much will be able to recover, that will be used for the next process, and it will increase the economy of the micellar-enhanced ultrafiltration process. Now, we will be discussing the last topic like this MEUF the metal ion and oxygen ions using mixed micellar system like this both CPC and SDS. Okay. So, cationic as well as the anionic surfactant mixture. So, we have tested also, and we found that the mixed micellar system is effective in separating both the cationic and anionic surfactants, because in this case in mixed micellar system both the cationic moiety and the anionic moieties are present in the system, but at the same time the throughput of the system actually will go on decreasing as the huge amount of gel layer will be formed over the membrane surface, and it will give the additional resistance through to the water flux through this membrane. Okay. Now, we have this CPC concentration is 10 kg per meter cube and SDS concentration is 25 kg per meter cube, and in that case whenever we have seen that the observed retention values are almost always more than 97 or 98%, but with the increase of the solute concentration the flux will go on decreasing slowly and slowly due to the generation of the gel layer over the membrane surface, and at the same time we can say this one permeate flux value, that is we can say it is decreasing, and we can say viscosity will go on increasing with the increase of the solute surfactant concentration in the this one feed. In this case the membrane was taken as 5000 Dalton. So, we can say the throughput value should be higher than 1000 Dalton membrane, because the pore diameter of the 5000 diameter membrane is very high, or in other words we can say the membrane permeability value of 5000 Dalton membrane is much more higher than the membrane permeability value of 1000 Dalton membrane. So, now we have these two different surfactants cationic and anionic. So, we need these two different processes for the regeneration. That is why suppose we have this inside this feed we have surfactants and say cationic and ionic, say we can see this CPC and SDS, and these all solutes are there. Then through this MEUF process we have two different, one is retented that will coming back to the feed chamber, and the permeate will be first treated like this. Whatever we tested for the separation of say SDS, then we have this precipitate and this filtrate. From this we can say this one whatever the filtrate is there, from this we can say chemical treatment 3 will be again will be doing this chemical treatment 4 to get the surfactant rich filtrate, and that will be reused. Again whatever the we can say this one solubilized form actually will be getting from chemical treatment 2, that will be used again to the membrane separation process. So, first one or two process will be used to get SDS, and this third and fourth will be the regeneration of CPC. Okay. So, that is why the processes will be like this, first 1 and 2 whatever we have discussed this for SDS, whatever the equation was there, same thing. For third you can say this potassium iodide will be adding with CPC, and for whatever the CPI is there, we discussed this on the beginning, that for cationic surfactant the same thing is actually will be doing, or we can say this one reaction 1 2 will be for anionic surfactant, reaction 3 4 will be for cationic surfactant, and we will be able to get the we can say this on both the surfactants from different streams, and then we will be reusing these surfactants for the membrane separation process for the mixed micellar system. Okay. So, this is the we can say this performance of the chemical treatment 1 to 4, and you see this one for SDS overall separation with respect to permeate is 87%, for CPC it is 81% almost. So, we are now able to reuse the surfactants which are coming out through this permeate, that will be recycled back to the system for the next process. Now, we will be solving one problem on the we can say using this SDS as the micellar solution, and this one for that case phenol is the target component. So, phenol is removed from the problem is like that, phenol is removed from SDS micellar solution of 10 kg per meter cube, and feed concentration of the phenol is 20 milligram per liter. Solution of the phenol in the micellar is 2.34 milligram per gram of the surfactant. Then the solution isotherm is given as like Langmuir type, S is equal to Q into B1 into Cp by 1 plus B1 into Cp, that B1 actually is the we can say this one solubilization constant, and Q is the we can say this one solubilization capacity, S is we can say this one isotherm, and Cp is the solute concentration in the permeate. So, that Cp is we can say 2.3 kg per meter cube, and mass transfer coefficient K, that is we can say 2.5 into 10 to the minus 5 meter per second. Okay. Now, we need to find the permeate flux value and the permeate concentration of the phenol. Okay. But we do not know the solute concentration of the phenol, this phenol concentration in the permeate. Okay, that we need to find out, then only we will be able to get the what is the we can say, if we know the retention, from there we can get the solute concentration in the permeate. Okay. Now, we will be solving this one. So, here we can say as the this is we can say it is the gel layer actually is formed. So, gel layer concentration is given. So, we will be using this gel layer theory, like this we can say this one flux Jw will be equal to K into Ln Cg by C0. K is given as 2 into 10 to the power minus 5 and Ln Cg is given as Cg 280 kg per meter cube, 280 divided by that is C naught is equal to 0, 10. So, it is coming out as flux is coming out as 6.66 into 10 to the power minus 5 say meter cube per meter square second or meter per second. So, the first problem is very straightforward. For second problem, we need to get the concentration of the solute in the permeate. So, for that we have this solubilization isotherm is equal to Q into B1 into Cp by 1 plus B1 into Cp. Okay. So, that solution isotherm is given as 2.34 into 10 to the power minus 3 is equal to Q is given as 0.1 into 9 into 10 to the power minus 2 into Cp we do not know by 1 plus 9 into 10 to the power minus 2 into Cp. Okay. So, then we can say this one 2.34 into 10 to the power minus 3 plus 2.34 into 9 into 10 to the power minus 3 10 to the power minus 2. So, it will be coming as 2.1 into 10 to the power minus 4 into Cp, that will be like this 9 into 10 to the power minus 3 into Cp. Therefore, Cp will be equal to 0.266 milligram per liter. Okay. So, now that is the concentration of the solute or we can say phenol in the permeate, whatever this permeate concentration of the solute. So, it is this is we can say this one permeate concentration of the phenol in the permeate. Okay. So, then from there we can say this how much retention actually we have. So, we can say we can do observed retention. Okay. So, that is RO is equal to 1 minus Cp by C0 into 100, that is coming out 1 minus 0.266 divided by 20 into 100. So, that is coming out as 98.67%. So, this is we can say the observed retention of the membrane, or we can say this the observed retention of phenol using this membrane is 98.67%. Okay. So, thank you very much. So, in the next class we will be discussing about adsorption and ion exchange.